Okay, hello everyone in a new video. So we have reached part 2 of chapter 8, which is the chapter of Newton's second law for rotation, and eventually we were solving this exercise, which is exercise number 1, and it is left to complete figures D and E. As you can notice that this is exercise number 1. So in this exercise they are telling me to determine the resultant moment of the forces shown in the figures below. So we are in figure D. So here we have two forces, F2 and F1, and the rod that is massless is allowed to rotate around the axis delta. So let's start by calculating the moment of the force F1 produced by F1 on the axis delta, which is equal to F1 tangential multiplied by D, in which D is the distance from the point of application of F1 to the axis of rotation, which is given by 5. So F1t, now this is the projection of F1 on the tangential direction, which is the tangential component. So let me specify the tangential component. Since this is the radius of rotation, suppose it's rotating around the center, then this is the tangential, which is the tangent to the radius, then this is the tangential direction. Similarly here later, because we will project also F2 on the tangential direction, so this is the radius of rotation, suppose around the axis delta, so this is the tangential direction, which is the tangent, like this. So now let me specify the positive direction. This is the positive direction, which is anti-clockwise. Now in this case, notice that F1 will try to rotate around the axis of rotation like this, which is in the positive direction. So it's a plus multiplied by its magnitude, which is given by F1, multiplied by the cosine of the angle between F1 and the tangential component. If this is 25, then this is 90 degrees minus 25. So cosine of 90 degrees minus 25, no need to calculate it because this is simply F1 sine 25. Now notice that here I didn't place pi by 2 because this is expressed in degrees, okay? So if this is expressed in radians, then I would have placed this value in pi by 2. Now let me calculate sine 25. Here you need to make sure that your calculators are adjusted to the degrees. So sine, okay. Now the moment of the force F1 around the axis delta is given by this, which is this, multiplied by D. Now the value of F1 is given by 5. This is sine 25 multiplied by the value of D, which is 5. Plugging this on the calculator, then the value of the moment of F1 produced on the axis delta is given by 10.57 Newton meter. Then the moment of F1 produced around delta is equal to 10.57 Newton meter. So this is it for the force F1. As for the force F2, we have that the moment of the force F2 around the axis delta is equal to F2 tangential multiplied by D, and in this case D is also given by 5 meters. So now F2 tangential is the projection of the F2 force along the tangential component, which is this. So notice that if this is the positive direction, F2 will try to rotate the beam like this, which is around the axis delta, so it's a plus in the positive direction, multiplied by F2 multiplied by the cosine of F2 and the tangential. This is 45, which is pi by 4, or let me say cosine 45 degrees. Now also here we could have computed this angle, which is 75 degrees, and this is cosine of 75, it's the same. Now okay, so replacing this here, we get that the magnitude of F2 around the axis delta is equal to F2 cosine 45 multiplied by the value of D, which is equal to 56 newtons multiplied by cosine 45 multiplied by the value of D, which is 5. On the calculator, 56 multiplied by cosine 45 multiplied by 5, then it's given by 197.99 Newton meter. Now, the summation of moments around the axis delta is equal to the moment of the force F1 along delta plus the moment of the force F2 along delta. So 10.57 plus 197.99, then this is equal to 208.56 Newton meters. Then this is the value of the summation of the moments acting on the beam in figure D. Now as for figure E, so we have three forces, F1, F2, and 3. Let me start by the force F1. So the moment of the force F1 is equal to F1 tangential multiplied by D, in which D is the distance from the axis of rotation to the point of application of the force F1, which is given by 5. Now F1t is the tangential component of the force F1 along the tangential direction. So let me state the tangential direction. In this case, this is the axis, this is the center. So this is the tangential direction. Similarly, for the force F3, this is the radius. So this is the tangential direction. So notice that now in this case, if this is the positive direction of rotation, so F1 will try to rotate in the positive direction, which is like this, in the negative direction. So it is minus the magnitude F1 multiplied by the cosine of the angle between F1 and the tangential direction, which is given by eventually 45 degrees. So plugging this expression here, what you will get is that the moment of the force F1 along the axis delta is equal to minus F1 cosine 45 multiplied by D. So minus the value of F1 is 15 multiplied by radical 2 over 2, which is the value of cosine 45 multiplied by 5. Plugging this on the calculator, so the moment of the force F1 around the axis of rotation delta is given by minus 53.03 Newton meter. So now as for the moment F2, it's always better to write the vectors in this case. Which is equal to F2 tangential multiplied by the distance D. The distance C from the F2 to here, the point of application, is given by 5. So F2 tangential is equal to, notice that in this case this force will rotate in the positive direction like this. So it's a plus F2 multiplied by the cosine between F2 and the tangential direction. So if this is 40, then this is eventually 50. So cosine 50. Now F, the moment of the force F2 around the axis delta, is equal to plus F2 cosine 45 multiplied by D, which is equal to 17 multiplied by radical 2 over 2 multiplied by 5. Therefore, plugging this on the calculator, 17 multiplied by 5 by radical 2 over 2 is equal to 60.1 in Newton meter. So the moment of the force F2 around the axis delta is equal to 60.1 in Newton meter. And now regarding the force F3, so the moment of the force F3 around the axis delta is equal to F3 tangential multiplied by D, which is equal to, now the value of D between F3 and the axis of rotation is given by 5. So F3 tangential is equal to either plus or minus sign. Notice that F3 in this case will rotate around like this in the positive direction. Magnitude F3 multiplied by the cosine between the tangential and F3, which is given by 30 degrees. So now in this case the moment of F3 around the axis delta is equal to plus F3 cosine 30 multiplied by D, which is equal to 17 multiplied by radical 3 over 2 multiplied by 5, and in this case the moment of F3 around delta is equal to 73.61 Newton meter. And simply now the resultant of the forces around delta is equal to moment of F1 around delta plus moment of F2 around delta plus moment of F3 around delta, which is equal to minus 53.03 plus 60.1 plus 73.61. And on the calculator, which is equal to 80.68 Newton meter. Okay, so this is it for this exercise. Now we are going to discuss section number 2, which is given by rotational and translational equilibrium. Translational Previously, we have discussed the translational equilibrium, and it's given by sum of forces is equal to zero vector. So this is a vectorial equation and we know how to deal with it. Now in the case of rotational equilibrium, now without surprises we can directly deduce that the rotational equilibrium is given by summation of moment around any axis delta is equal to 0. And here no need to place any vectors, because as we have seen that although the moment is coming from a vector quantity which is due to a force, but it is a scalar quantity, okay? So, and here take into consideration that we are talking in 2 dimension only, not 3 dimension or 4 dimension. So this is the rotational equilibrium, okay? And if we are talking about analogy between rotation and translation, So in this case, the force is simply replaced by a moment. Okay, this is similar to the fact that the displacement x was replaced by theta, the speed was replaced by theta prime, and the acceleration was replaced by theta double prime. And here for sure we are talking about the tangential acceleration. So probably in this chapter we'll go over these again. Okay, and now let's solve the following exercise related to the rotational equilibrium. So exercise 2, they are telling me determine in part 1 the magnitude of the force F needed for the system to attain equilibrium. So here when they are talking about the equilibrium, they mean two things, either rotational equilibrium or translational equilibrium, and one should understand that these two are independent of each other. Okay, so a system may be at translational equilibrium, but at the same time may be maybe not at rotational equilibrium. Now notice that if you consider this beam, let's start by figure A. So in figure A, this beam is hinged, so it is only allowed to rotate around the axis delta. So it can rotate, but this beam cannot move in a translational way. So this beam cannot move upward because it is attached here, fixed here. It can rotate like this, and it can rotate like this, but it cannot move left or right. It cannot move up or down. Okay, so when they are talking about equilibrium, they are asking me the rotational equilibrium because these are already in the translational equilibrium. So we need to determine the magnitude of the force F needed for the system to attain equilibrium. So we will say at equilibrium we have that the sum of moments is equal to 0. So now the moment, what are this around the axis delta? So what are the moments that are acting on the beam? We have the moment due to the force F1 around delta plus the moment due to the force F2 around delta equal to 0. Now we are interested in determining the expression of each one. Sorry, here we don't have F2, we have F. So let's start by the moment of the force F1 on delta, which is equal to, so F1 tangential multiplied by D, which is equal to, here I wanted to say something about the equilibrium. I'm not sure about the fact that if it, okay, so let's discuss this later. Okay, nothing. Now F1 tangential, so F1 tangential multiplied by D. Now, so this is, what is the value of D? Now the value of D in this case is given by 5 meters. So F1T now in this case, if this is the positive direction of rotation, so F1 will rotate the beam like this, which is in the positive direction. Now this is F1, let me specify the tangential direction. If this is the center of rotation, sorry, radius, so this is the tangential direction. So cosine of the angle between F1 and the tangential direction, which is given by, in this case, 60 degrees. Now M F1 on delta is equal to, let me write it here, plus F1 cosine 60 multiplied by D, which is equal to 11 multiplied by half multiplied by 5. Plugging this on the calculator, which is given by 27.5 Newton meter. Okay. Now as for the moment of the force F produced on delta is equal to, so it is F tangential multiplied by D, and in this case the distance between F and the axis of rotation is 5, which is this distance. The distance from the point of application to the center is given by 5. Now as for F tangential, notice that F in this case will try to rotate the beam in the negative direction, multiplied by F multiplied by the cosine. So notice that in this case F completely lie on the tangential direction, so no need for the cosine. So in this case the moment of F over delta is equal to minus F multiplied by D, which is equal to minus 11 multiplied by 5. So here, sorry, we don't know the value of F, so it's equal to minus F multiplied by 5. So now, replacing this expression and this expression, so notice that here I didn't express any unit because it's expressed in terms of another variable. Replacing them here, because we know that M of F1 on delta plus M of F on delta is equal to 0, which means minus F multiplied by 5, which is equal to 27.5 minus F multiplied by 5 is equal to 0, and we are solving for F. So what's the type of this equation? This is a linear equation and one unknown. So directly the value of F is given by 27.5 divided by 5. And plugging this on the calculator, then the value of the force that attains equilibrium is given by 5.5 newtons. And the thing is that, because what I was thinking about, because it is in translational equilibrium, one can try to project F1 on the y-axis, and one can use the following equation, that F1 cosine 60 degrees is directly equal to the value of F, to find the value of F1. But in this case, this works here, but it doesn't work in other places. Okay, so here, as I said previously, that we are interested only in a rotational equilibrium because the beam is already cannot move in a translational direction. Okay, so maybe in this case F1 cosine 60, which is equal to F, works in order to determine the value of F. You can try that 11 times radical 3 over 2. So let me try. Okay, 1 second. Just let me make sure of the calculation. Yes, if you try 11 multiplied by half, it will give you 5.5 newtons. Here the condition of translation equilibrium works, but in other cases it doesn't work. Okay, so yes, here we are interested in the rotational equilibrium. So now let's move to the figure B. I repeat that we are interested in the rotational equilibrium because the beam already cannot move. We are discussing in which the beam cannot rotate. So we are in figure B. So we need, okay, let me continue the question here. So F is equal to 5.5 newtons. And in number 2 they're asking us that the direction of the rotation caused by F. So in this case the direction is like this. So the direction is clockwise direction. Okay. Now as for figure B, I repeat that we are interested in the rotational equilibrium. So we will say at equilibrium we have that the sum of moments around the axis delta is equal to 0, and here we are talking about the moment of the force F1 produced around delta plus the moment of the force F2 produced around delta plus the moment of the force F produced around delta. And let's determine each of the following expression, knowing that the value of F, which means the magnitude, will appear eventually in this term. So the moment of F1 around delta is equal to F1 tangential multiplied by D. In this case, D is given by 5 meters from the center to the point of application of F1. We will take directly the tangential direction to be this. Let me specify the tangential direction here and here as well. So D is equal to 5 meters. F1 tangential is equal to, in this case this is the positive direction, so it will try to rotate the system like this. So this is negative F1 multiplied by the cosine of the angle between F1 and the tangential direction, which is this, which is 50. So in this case the moment of F1 on the axis delta is equal to minus F1 cosine 50 multiplied by D, which is equal to minus 75 multiplied by cosine 50 multiplied by 5. Plugging this on the calculator is equal to minus 241.05 Newton meter. So this is the first moment or torque produced around the axis of rotation due to the force F1 on the beam. Now in this case the moment due to the force F2 on the axis delta is equal to what? It is equal to F2 tangential multiplied by D, and in this case also D is given by 5 meters, which is this distance, knowing that this is the radial direction, so this is the tangential direction. So F2 tangential is equal to, in this case it will try to rotate in the positive direction, so it's plus F2 multiplied by the cosine 45, which is this angle. So which is equal to plus 15, and we will say that the moment of F2 around the axis delta is equal to F2, which is 15, cosine 45 multiplied by D, which is equal to 15 now, multiplied by square root of over 2 multiplied by 5. On the calculator this is given by 53.03 Newton meter. Now finally, for the moment produced by the force F, so it is exactly the same, nothing will change. So the moment of the force F on delta, which is equal to F tangential multiplied by d, given that d is equal to 5 meters. F tangential, because it's trying to rotate the system in the negative direction like this, so it is minus f. It is completely lying on the tangential direction, so this is 1. Now in this case, the moment of f on delta is equal to minus f multiplied by d, which is equal to minus f multiplied by 5. And f is kept as a variable because f must be fitted in a linear equation. Now, knowing that the sum of moments around axis delta is equal to 0, which means that the moment of f1 on delta plus the moment of f2 over delta plus the moment of f3 on delta is equal to 0. So minus 241.05 plus 53.03 minus f multiplied by 5 is equal to 0, knowing that we are interested in determining the value of f. So in this case, if you rearrange the equation, so what we'll do here, I'm solving it directly. So you drag this to the right hand side, it will be f multiplied by 5, dividing both sides by 5. So the value of f in this case is given by 53.03 minus 241.05 divided by 5, which is equal to minus 37.604, so 60 in newtons. So the value of f is in newtons. Okay. So now what about number 2, the direction? Now since f, which is equal to minus 37.060 newtons, is negative, which means that because we know that the value of the magnitude is always negative, recall that in the case of this f means positive, which means that the positive direction of the force f is in this direction. F negative, which means that the direction of f must be and this is extremely important, must be opposite to that chosen in the figure. Then in this case it must be vertically upward. So this is vertically upward like this. This is the new direction of f. Figure is not drawn to scale and this direction of f is wrong. Now in this case, f will try to rotate the system in the positive direction, so which means anti-clockwise. The direction of rotation caused by f is anti-clockwise. Okay. So that's it for me in this video, guys. Okay, before let me recall that whenever a magnitude, when we are solving and the value of the magnitude is negative, it doesn't mean that we have done something wrong. Simply it means that the direction of the chosen force must be reflected, which means it is taken to be the opposite. And now if we take F and the direction of rotation caused by F is anti-clockwise direction. So here we can do a remark. So either we take F to be minus 37.60 newtons and with the direction to be downward, or we take F to be 37.06 newton and with the direction to be upward. Okay, so both of these are correct, but we always are interested in this one because we know that the value of F is positive, which represents a magnitude and not a component. So that's it for me in this video, guys. In the next part we'll complete solving exercises on this chapter.